All right. Hello, everyone. Welcome to our next recitation on Mechanics and Materials 1. We also have 4 exercises to get today to go through them together. This is the first one. These 4 exercises, they will cover, or they are dealing with the topic torsion. All right. So you have a steel assembly, or you have this picture. There is a shaft. There is a solid shaft at the center, AB, surrounded by this tube from, let's say, B to C. The shaft is made of A36 steel, and for that, we know in particular that, let's say, the shear modulus G is 75 gigapascal. The outer radius of this shaft is 25 millimeters, and it has a thickness of 3 millimeters. So basically, you know that its inner radius is 22 millimeters. Okay, this is for the tube, right? Okay, the shaft itself, it has a diameter of 25 millimeters. So its radius is, on the other hand, let's say its external radius is 12.5 millimeters. Now, what we do, or the loading that we apply a torque here, as shown in the figure, at C, and you are asked to calculate the rotation of the tube's end C, so here. We want to know what is the angle of twist at C, all right? Now, this is a very interesting exercise and kind of different from what you have done before, or what we have done before, because you see, usually when we had a shaft, we would say, for instance, this is our coordinate system, and then we go forward, right? And then we have a point here, maybe. So, and then you can always say what is the, let's say, relative rotation of those points. Now, in this one, it's kind of similar in that sense, except that here you kind of go back, okay? So what I'm trying to say is that you need to kind of conceptually try to understand this. Let's say you apply this torque, okay? This torque is going to rotate C with respect to B, right? Let's say 2 degrees. But then the same torque would also rotate B with respect to A, let's say 5 degrees, okay? And then you need to add that 5 plus this 2 to get, I don't know, 7, and that would be the rotation of C. Does that make sense? I mean, usually when we had these sort of problems, the points, they were always along the same line, so this is kind of like that. All right, so what we want to do is to calculate phi, or angle of twist, at C. But then remember that when we say, or when we want to calculate the angle of twist at any point, we should always calculate it with reference to a fixed point. So the fixed point here is point A. A is supported, right? So this basically is phi of C with respect to A. All right. Now, that itself means phi of C with respect to B plus phi of B with respect to A. Does that make sense? Okay, so that's all you need to do. I just remind you of this formula that we had. Usually, I don't know, for a distributed load, let's say if you want phi of, let's say, point alpha, or maybe I write it like this, point beta with respect to alpha, you would integrate from alpha to beta of internal torque divided by, let's say, Gj, which they could also be a function of x, by the way, dx. Okay? This is the only thing you need to be kind of careful about. So if you think about going from alpha to beta, that means your dx should be such that it goes from alpha to beta, right? So the positive direction is chosen like that. All right. Okay, so what you need to do is to just calculate these two angles. So phi of C with respect to B would be T in that CB member, or let's call it BC for, LBC divided by GJ. So GBC, JBC. That's one side of the problem. The other side is phi of B with respect to A. That is TAB, LAB divided by GJ. Now, G is simple. It's given, what did we say? It's 75 gigapascal. And it's constant for both problems. J. For AB, we have a solid shaft with the radius of 12.5. So JAB is pi over 2, 12.5 millimeters to the power 4, and 12.5 millimeters, 0.0125 meters to the power 4. So that's for AB. For BC, it would be pi over 2. The outer radius, the outer radius from B to C, that is 25 millimeters. So 0.025 to the power 4 minus 0.022 to the power 4. So remember, J for hollow shafts was pi over 2, CO to the power 4 minus CI to the power 4. All right? Now, the length LBC is 100 millimeters. And here, from A to B, that's 250 millimeters. So how about the torque? The torque between C and B, it's 25 Newton meters. So at the end B, you would get 25 Newton meters as a reaction to this, which that in itself would count as a reaction, as an action to AB, right? So at B, basically what happens is that this torque would be transformed to AB, okay? So it rotates also that in the same direction. Okay, so T here is 25 Newton meters, and here is also 25 Newton meters. Does that make sense? So just you need to kind of pay attention that they rotate in the same direction, right? So whatever happens with this torque, and if it turns, I don't know, 2 degrees, and that shaft at the bottom, it turns also 2 degrees, they add together and they become 4 in the same direction. Okay, so that's it. So basically, you want phi of C with respect to B, that's it. B with respect to A, it's this one. You add them together, and you would have phi of C. So phi of C, if you insert these numbers, would be 0.00237 radian, or otherwise 0.132 degrees. So if you multiply it by 180 divided by pi, obviously. Also, just for your own calculations to check, this phi of C with respect to B would be 0.0001357 radian, and this one would be 0.02173 radian. All right, so this was the first exercise. Do you have any question? Is that all clear? Okay, so the second exercise is this. We have a shaft that has a changing cross-sectional area. Now, for this shaft, the curve here has the equation y equals e to the power ax. And you can see in this coordinate system, so this is x, this is y. So basically, y is the radius of the shaft, right? So this equation is essentially telling you that r is e to the power ax, okay? So if x is 0, this would be 1. So essentially, we know here at x0, radius is 1, for instance. And then for every point, you can find it as a function of x, right? So that's that. Now, for this shaft, for a given torque T and shear modulus G, you want to calculate the angle of twist. The angle of twist, again, remember the formula that we just had. Let's say phi from A to B. In this case, I don't know, I can say phi of B with respect to A, or from A to B. Again, remember, it's from A to B because x is directed from A to B, and that gives you phi of B with respect to A. That would be integral from A to B of T as a function of x divided by G as a function of x, J as a function of x dx. So in this particular example, T is not a function of x. In fact, T is just constant, it's T. G is also constant, it's just G. Only J is a function of x. Now, what is J as a function of x? It's pi over 2 radius to the power 4, but the radius itself is a function of x, which is the same as I. So it's pi over 2 e to the power ax to the power 4, or pi over 2 e to the power 4ax. So this would be your j here. Now, j is in the denominator. That tells you you can basically have this to the power -1 and write it here as being, let's say, upstairs at the nominator. Okay, so we do that. So basically, we come here and say phi b with respect to a is integral from a to b would be from 0 to L. We know the length is L. Now, t is just t. Again, g, just g. And instead of j, I am going to write 2 over pi e to the power -4ax dx. Right? Instead of j as being in the denominator, I can write it like this. Now, these are constants. They come out. You would have 2 times t divided by pg integral from 0 to L of e to the power -4ax dx. And if you remember how to integrate that exponential function, it's not that difficult. It's basically e to the power -4ax divided by -4a. So this would be from 0 to L. And if you just insert 0 and L here, okay, obviously when you put L, you just get L here. If you put 0, you get 1, right? And then there is this minus sign, so you kind of expect to see something with the 1, with 1 being a plus number, right? So because the second one is multiplied by a minus here. So you get this 2t divided by pg, that's the coefficient we had, times 1 minus e to the power minus 4al divided by 4a. So I am missing that minus now, and that's it, basically. That's the answer. If you want to kind of make it maybe more simple, you can also cancel this, and you get t divided by 2pga 1 minus e minus 4al. All right? So that's the second recitation. Do you have any question? Okay, so the next one is gonna take some time, and it has some, let's say, some weight to it. We should be careful about this one. You have a shaft here with a constant radius c made from this, let's say, from a constant material, or it has a constant g. So g and j are constant. They are not a big problem here. On top of that, you apply a distributed torque as given in this equation. We want to calculate the reactions at the supports A and B. Okay? So you can immediately see that this is fixed at both ends. So you have two unknowns, but we have one equation. The equation that we have is equilibrium of moments, or in this case, it would be the equilibrium of torques, right? So whatever you have at that A and B, if you add it up to whatever you apply externally, you should get 0. That is your equilibrium, which is your first equation. So we are going to begin with that. And also we need to pay attention to the signs. So see, the x coordinate is here. So we measure it from the left-hand side, right? That means our, let's say, our x coordinates looks like that. So we look from that end to, to think what is clockwise and what is counterclockwise. Now, in this coordinate system, if you look at all these little t's that you have, you can see they are both being basically, sorry, these little t's that you have, they are all being counterclockwise, right? So if we want to draw like a one-dimensional version of this, and I always encourage you to do that, always try to write or to draw a one-dimensional version of this. These counterclockwise torques, because they are counterclockwise, according to our convention, you can assume they are all plus, right? So this is the T that we have through the shaft. Now, obviously, again, think of it as just being forces. If you had a distribution of forces like that, you would need two forces in the opposite direction on the both ends to compensate for it, right? In this case, this would be TB and TA. Does that make sense? Which would be clockwise. So at B, we draw TB like that. It would be a clockwise moment. It doesn't matter how you draw it, but I'm just trying to say that from the picture, you can imagine TB would be clockwise. You could just draw it counterclockwise, and if you solve it correctly, you end up with a minus number, okay? But let's say from the picture, we kind of guess that it must be clockwise, so why not start with that? Okay, so our equilibrium equation. The equilibrium equation is our first equation, and that would be, as I said, it's like sum of the moments is 0, which in this case, it means sum of the torques are 0. So what are the torques that we have here? There is this external torque that we apply, okay? But pay attention, this is applied as a distributed torque. This is torque per length. So the integral of that would be your total torque. Does that make sense? So I am going to just call that T external, okay? And that is counterclockwise in our coordinate system. It's a plus. A and B, they are clockwise, so they come with a minus, and that's 0, okay? So this is equilibrium of external torques. Again, what I call here Tx itself, it must be an integral of those little t's. Okay, so let's write that. T, external t, it would be integral of that t, small t, dx, from 0 to L. Does that make sense? So that would be integral from 0 to L of T0 1 plus, I don't know, x over L squared dx that gives you integral from 0, well, we can integrate it. So integral of, let's say, 1 would give you x. This gives you x cubed divided by 3 times L squared. So this would be T0 x plus x cubed divided by 3 L squared, right? And this is from 0 to L. Obviously, at 0, you just get 0. So at L, you get T0 times L plus L cubed divided by 3L squared. That's 1 over 3L. So that's 4 T0 divided by 3 times L. Does that make sense? Okay, so this is our T, what I call external T torque, all of it, for equilibrium equation. Okay, so so far so good. We have our equilibrium equation. We know exactly what that is. So we just let me write it here. We know minus TA minus TB plus 4 over 3 T0L is 0. That is the first equation. And as I said, this is equilibrium. Now, we have two unknowns, TA and TB. In order to calculate them, we need a second equation, and that would be our compatibility equation, okay? So we need a second equation, which is our compatibility equation. So what is the compatibility equation in this example? You see, these 2 points, they are fixed at A and B. So phi of A with respect to B is 0, right? So that becomes your compatibility equation. You can say phi of A with respect to B is 0. And then again, remember when I say A with respect to B, this means from B to A, so you shouldn't be confused with the alphabetic letters. It's from B to A because X is going from B to A, okay? All right, so we just need to write this or to impose this, and that would be our second equation. However, if you want to do that, you realize that now you have a system which can be also split into two systems, so we use the principle of superposition for that. All right? So we assume that instead of just calculating that angle for the system that you have here, I will split this system into two systems, and then separately I calculate phi of A with respect to B for each of them, and I add them and I make them 0. Does that make sense? So what I want to do is basically this. I would say, I'm going to draw this thing, and then in one of them, in both of them, I assume point A is fixed, right? So this is point A on the right-hand side. In one of them, I have my little distributed torques. So let's call that system 1. In the other one, I have only my torque at B, okay, my TB. All right, so if you also look at the system then and the way we drew TB, you would expect that TB to be here, okay? So this was our TB, right? This is the way we drew it up there, okay? So for both of these systems, we want to calculate of phi A with respect to B. And then adding them should give us 0. Okay, so far is everything clear, I hope, right? For the first system, if you think about, you should do the same thing for both of them, but let's look at the first system first. So you cut it here, right? And we need to calculate the angle for any, let's say, for any distance x from, so let's say this is our x coordinates. For any distance x from B, if you want to calculate the angle, that would be the integral from that point to x of tx dx divided by gj. That's clear, right? Now, in this example, what is the Tx? This is internal torque, okay? Does that make sense? So for the internal torque, if you think about it, we just draw it like that. So that internal torque plus this integral, it would be 0. Does that make sense? So we write the equilibrium to get that. So Tx, which is the internal torque, plus integral from 0 to x of that little tx dx, it's 0. We are, by the way, we are in system 1, right? So this is in system 1, assuming that there is no TB. Does that make sense? Okay, now, what is that T0, that T as a function of x? It's basically what we just had here, and the integral is exactly that. So, okay, let's just keep it like that, and then assuming that you did the integral, let's just do the proper integral. It would be 0 to x, sorry, not 0 to x anymore. We just integrate it. It would be minus T0 x plus x cubed divided by 3l squared. Okay, and then if it is from 0 to x, it's exactly the same thing. So this is the answer, okay? So this is t as a function of x. Now, what you need to do is to insert this into this integral. And we do exactly that. So if you do that, you get phi of x is integral from 0 to x of that t, which is minus t0 x plus x to the power 3 divided by 3l squared dx. And then there is a 1 over gj that you can just write it here, okay? So those are constant. I took it out. So if you now do that, you get here x squared. Here you get x to the power of 4 divided by 4. So you get 1 or minus 1 over gj times t0 times x squared divided by 2 plus x to the power 4 divided by 12 L squared. Okay? So this gives you the angle of twist at any point x. But what would be the angle of twist at point A? This would be the same, this thing basically at A, right? For A, x is L. Does that make sense? So we know the angle of twist for any point x starting from B. If we insert x equals L, we get the angle of twist at A. Or let's say A with respect to B. Okay, we know A is fixed, but the relative angle of twist. Okay, so if you do that, so I'm going to kind of simplify this and clean it up. So all you have to do is to insert L here. If you insert L, you get L squared divided by 2 plus L squared divided by 12, right? So 1 over 12 plus 6 over 12. So 1 over 2 is 6 over 12. So this gives you 7 over 12 L squared, all right? So basically what we get here is that phi from system 1, if you want this phi of A with respect to B, you get, what did I say, minus t0 divided by gj times 7 over 12 L squared. All right? So this is from the first system here. Okay, so I'm going to clean this up and proceed. Do you have any questions so far? Okay, so we know how to handle with the distributed load, which was the more difficult part of this. And now we have the answer for the first part. So we got that. It's this. Now, for the second one, for the second system, we do exactly the same thing, and it's much easier. So if we cut it here, and if you think of, let's say, your internal torque, so again, this would be also t as a function of x. This was also t as a function of x, right? If you look at it from this direction. So for our second system, what is t as a function of x? Remember, this was the first step that we also asked ourselves here. What's that? Tx minus tb would be 0, right? It's just a simple equilibrium. So basically, Tx would be Tb. It's a constant. So if you think of that integral, it basically becomes a constant. So you can use our relationship that we always like to use. So you would say phi is simply t, or let's say phi of x is simply t x over gj. Okay, which in this case it would be simply tb x over gj, right? And if x is L, then we talk about point A. So at A, so phi A with respect to B for system 2 is then TB L over GJ. Okay? So now you have this, you put them into this one, you add them up, you set them to 0, and that is basically your second equation, and you're done. So if you do that, then you immediately get this minus T0 divided by Gj, 7 over 12 L squared. Somewhere, I think, no, it's good. Okay, so that's that, plus TB L over Gj is 0. And from that, you get TB equals seven over 12. So Gj cancels out immediately, right? So you get 7 over 12 T0 times L, which makes sense. T0 was moment or torque per meter, right? Small t. The dimension-wise, it makes sense. You need to multiply it by length. Okay, so that's that. Now you have TB, and remember, this was your first equation. This. Now, if you just insert TB into this, you also get TA, okay? And TA would be 3 divided by 4 T0 times L. Okay? So all you need to do is to insert this into your first equation, and you get TA equals 3 divided by 4 T0 L. Okay, so I think this is as complicated as one of these torsion exercises can get. It's a very, very good exercise for that matter to kind of make sure you understand every steps, okay? It has distributed load, and it has also this statically indeterminate discussion. Do you have any question? All right, so that was the third exercise. The last one is pretty simple and straightforward. You have a steel tube with an elliptical cross-section, and the dimensions are shown here. If the allowable shear stress is 56 megapascal, and the tube is to resist a torque of 340 Newton meter, determine the necessary dimension B. The mean area for the ellipse is given also here. So there is nothing overly complicated about this. It's just to have also a problem that does not deal with our regular cylindrical shafts, but rather with this discussion of thin-walled cross-sections, right? So if you remember, for these sort of problems, we say tau average is related to T by the formula here, so T divided by 2T AM, and AM was the main area, which in this example, you actually know it's pi P B times 0.5 B. Okay, so um, as you can see, AM is a function of B. Thickness is given, is 5 millimeters. T is 340 Newton meter. We want toe average to be smaller than the allowable shear stress, which is 56 megapascal. So all you have to do is to set toe average here to 56 to find, let's say, the smallest B, okay? That's the idea, or the necessary B. Okay, so you just set toe average to be 56 megapascal, and that gives you B equals 0.0197 meter, or otherwise 19.7 millimeter. All right? Okay, so pay attention again. Here, B is in the denominator. So if you have a larger B, a B that is larger than this, your denominator gets larger, so your stress gets smaller. That's a good thing, right? So basically, this tells you the smallest B you can do, and you will be still within the limit. So that's the answer to this question. Is that clear? All right, so these were the 4 exercises for this recitation.